Welcome you all to this lecture on mathematical induction. This is going to be the first lecture on the concept of mathematical induction. To begin with, let me make some remarks. By this time, you might have observed that theorem and proof are two most important words in the vocabulary of mathematics. They are so inevitable that one can even treat them as soul and heart of mathematics. By the way, when I say a theorem, formally I mean to say a statement that can be shown to be true, and by a proof we mean a valid argument to demonstrate that a theorem is true. And there are various techniques to prove a theorem, and basically mathematical induction is a proof technique. Let me elaborate a bit more. Mathematical induction is one of the various proof techniques which is commonly used to prove a statement involving a natural number. Let me give some examples. Consider the statement sum of first n natural numbers is n into n plus 1 by 2. To put in symbol, 1 plus 2 plus etc. up to n is equal to n into n plus 1 by 2. And this is a statement involving variable n, where n is a natural number. Suppose we wish to prove this statement is true for any n, we can use mathematical induction. Let me continue to give you a couple of examples where mathematical induction can be used. Consider the statement for a positive integer n, n cube minus n is divisible by 3. Again, you have a mathematical assertion involving a natural number. We demand that you have to prove this statement is true for any n. We can resort to the method mathematical induction. Let me give another example. Those who are familiar with set theory might have come across this result. A set with n elements has 2 power n subsets. Again, you have an example of a statement involving natural number n, and we wish to prove this for any n where n belongs to capital N, the set of natural numbers. Maybe there are many proof techniques. However, in this example also we can use mathematical induction. Informally, mathematical induction can be demonstrated by referring to sequential effect of falling dominoes. Suppose that we have infinite number of rectangular tiles which is placed vertically. Let us say I have 5 here, you imagine there are infinite number, in such a manner that when I push the first tile in a specific direction, all the tiles will fall. To absolutely make sure that this happens, it is enough to verify the following. 1. The first tile falls. 2. In the event that a particular tile falls, its successor, meaning the immediately next to it, fall. With these two, we can assert that every tile will fall. This is the underlying principle of mathematical induction. Let me put it slightly more formally. We are supplied with a statement or an assertion involving n, where n is a natural number. Let me denote that statement as P of n. And goal is to prove that P of n is true for all n belonging to the set of natural numbers. We can complete this in 2 steps. What are those steps? Step 1, we verify that P of 1 is true. And second step, assume that the given statement, namely P of n, is true for a specific value of n, say k. Assume that P of k is true for an arbitrary positive integer k. And prove that P of k plus 1 is true. If you recall the sequential effect of falling dominoes experiment that we have seen, the first step is equivalent to making sure that the first tile falls, and the second step is the event that if one tile falls, its successor falls. Once we complete these 2 steps, mathematical induction asserts that the given statement is true for positive integer. I should make a remark here. The second step involved in principle of mathematical induction, namely assuming that P of k is true for an arbitrary positive integer k and proving that P of k plus 1 is true, should not be confused with the fact that we are assuming P of k is true for every k. So, this is a warning. Second step is not that we are assuming P of k is true for all k. Recall that what we intended to prove is P of n is true for all n. So, if we assume P of k is true for all k, it is something like we are assuming what we are supposed to prove. But if you closely observe, in the second step, we do not assume P of k is true for all k, but what we do is we prove a conditional statement. If P of k is true, then P of k plus 1 is true. That is, we are not using begging the question or circular reasoning, or meaning to say we are assuming something which we are supposed to prove. No. I repeat, in the second step we assume that P of k is true for an arbitrary but fixed k, and using that assumption we deduce that P of k plus 1 is true. Now, first step says that P of 1 is true. Since P of 1 is true, applying the second step we will get P of 2 is true. Continuing in this manner, P of 3 is true and so on. P of n is true for every n. Of course, with a slight deviation from the rigorous mathematics, this is how mathematical induction works. And in what follows, let me introduce certain terminology usually used in connection with mathematical induction. I will put it as a remark. The first step which demands us to prove that P of 1 is true is generally referred to as basis step. And the second step, the crucial step in which we assume that P of k is true and we prove that P of k plus 1 is true, is referred to as inductive step. And in the second step, the assumption that P of k is true is generally referred to as induction hypothesis. To sum up, if we have a mathematical statement P of n involving n, and if we are asked to prove that P of n is true for every positive integer n, we can complete it in two steps, the basis step and the inductive step. The basis step demands one to prove P of 1 is true, and the inductive step demands one to prove P of k plus 1 is true with the assumption that P of k is true. Having said this, I should make another warning here. Though by the example that we have seen, namely the falling dominoes illustration, the first one falls. In the event that the first tile falls, the second one will fall, and this will continue so that the whole tiles will fall. Even though we understand mathematical induction in that manner, or we try to understand in that manner informally, a question arises, why mathematical induction, let me abbreviate as MI, is a valid proof technique. This is the question. In this regard, let me make the following comment. Generally, the word induction is used in the process where we get or we reach at a conclusion by generalizing from some specific example to the whole general case. That is the word meaning induction, but I would like to warn that mathematical induction is not a form of inductive reasoning. we are not generalizing from a specific example to a general case. For the time being, let us not dwell on the question which I posed right now, why mathematical induction is a valid proof technique. Let us not dwell upon why mathematical induction is not a inductive reasoning, but it is of course a deductive reasoning. We shall not discuss these things in this lecture, but our intention will be to explore this easy and elegant method of proof, mathematical induction, in various examples. What we shall do is to use mathematical induction to prove certain statements involving natural numbers. So, let us illustrate this with some examples. The first set of examples, we will use mathematical induction to arrive at some summation formulas. To be more clear, not arriving at summation formula, we are going to prove some summation formula using mathematical induction. Do you recall the first example that I told for a statement involving natural numbers? The example was sum of first n natural numbers is n into n plus 1 by 2. That is 1 plus 2 plus etcetera plus n is equal to n into n plus 1 by 2. What we have asked is use mathematical induction to prove 1 plus 2 plus etcetera plus n is equal to n into n plus 1 by 2 for every n from the set of natural numbers capital N. Okay. Let us look at how to go about. The statement which you are having involving n, let me call as P of n. So, P of n is the statement or the assertion or the proposition that 1 plus 2 plus etcetera plus n is equal to n into n plus 1 by 2. And what we are asked to prove is that P of n is true for all n. Let us use mathematical induction. Recall, mathematical induction involved two steps. So, let us start with the basis step. And requirement in the basis step is that we have to verify P of 1 is true. Now, in this example, P of 1 is sum of first one natural number. So, in left hand side we do not have a sum, but we actually have only one natural number, namely 1. So, the LHS is just 1, sum of first one natural number 1, and that is equal to 1 into 1 plus 1 by 2. This is obtained by just replacing n in the formula with 1, and you can see that 1 is same as 1 into 1 plus 1 by 2, because the 2 and 2 will get cancelled there, and this is a equality. That is, P of 1 is true. This finishes the basis step. Now, inductive step. What is the requirement in inductive step? We have to assume that P of k is true. and we have to prove that P of k plus 1 is true. Symbolically, assuming P of k is true is that 1 plus 2 plus etc. plus k is equal to k into k plus 1 by 2. This is the assumption for a specific k in n, arbitrary but fixed. Now, what we have to prove is P of k plus 1 is true. To prove that P of k plus 1 is true, note that P of k plus 1 is the statement 1 plus 2 plus etc. plus k plus k plus 1 is equal to k plus 1 into k plus 1 plus 1 by 2. So, this is what we want to prove. Okay, as usual, let us start from the LHS. 1 plus left hand side plus etc. plus k plus k plus 1. I am grouping 1 plus 2 plus etc. plus k plus k plus 1. Now, by the inductive hypothesis that P of k is true, we know that 1 plus 2 plus etc. up to k is k into k plus 1 by 2. So, the first bracket, the summation in first bracket boils down to k into k plus 1 by 2, and that is by induction hypothesis. By induction hypothesis. Now, let us manipulate the right hand side, which is equal to, by taking 2 as a common factor and so on, k into k plus 1 plus 2 times k plus 1 by 2, and this will be equal to k square plus 3k k square plus k plus 2k, which is amounts to 3k 2 by 2. And by factorization, you can see that this is k plus 2 into k plus 1 by 2. You are searching for numbers whose product is 2 and sum is 3, which are 2 and 1, and hence k square plus 3k plus 2 can be factorized as k plus 2 into k plus 1, and you have denominator 2. You can see that this is what exactly you have to prove. 1 plus 2 plus etc. plus k plus 1 is equal to k plus 1 into k plus 1 plus 1, which is k plus 2. So, thus assuming P of k is true, we proved P of k plus 1 is true. This finishes the inductive step. Therefore, by mathematical induction, P of n is true for all n. To be explicit, 1 plus 2 plus etc. plus n is equal to n into n plus 1 by 2 for every n from the set of natural number. So, this solves the first example. Now, let us continue with few more examples. Before getting into next example, let me make a remark. Note that mathematical induction is not a tool to get theorems about set of natural numbers. But it is a proof technique which can be used to prove a result once you have conjectured the result. Now, let me elaborate a bit more on this remark. Let us go back to the first example in which we used mathematical induction to prove that sum of first n natural numbers is n into n plus 1 by 2. Remember, we cannot come with this type of formula using mathematical induction. You cannot come with summation formula with the help of mathematical induction. Once you have this formula a priori, we can prove it using mathematical induction. To make it more clear, let us continue with the example. Conjecture or guess a formula for sum of first n odd positive integers. Verify your conjecture using mathematical induction. Here you are not supplied with a summation formula unlike in the previous example. Let us view a few instances or few examples. First, let us see what is sum of first one odd positive integer. One odd positive integer, the first odd positive integer is 1. So, there is no sum there. So, I can take the sum as 1. Now, you take first two odd numbers and let us sum it. First two odd numbers are 1 and 3. I sum it, I get it 4. Next, let us take first three odd positive integers, namely 1, 3 and 5. 1 plus 3 plus 5 is 9. We can go on. Let us do one more. Take first 4 odd positive integers, namely 1, 3, 5 and 7. Let us add it. You get 16 and so on. Do you see a pattern? Sum of first two odd number is 4, which is 2 square. Sum of first three odd positive integers is 9, which is 3 square. Sum of first 4 odd positive integer is 16, which is 4 square and so on. So, let us dream that this pattern will continue and let us make a conjecture. Sum of first n odd positive integers, namely 1 plus 3 plus 5 plus etc. plus I want nth odd positive integer. See, the second odd positive integer is 3, the third odd positive integer is 5 and so on. The nth odd positive integer will be 2n minus 1 and I guess 1 plus 3 plus 5 plus etcetera plus 2n minus 1 equal to n square. So, we did not prove this, but let us call it as a conjecture. Okay. Now, let us try to prove this using mathematical induction. Recall that mathematical induction can be applied when you have a statement involving set of natural numbers, and if you want to prove that it is true for all natural numbers. Here exactly that is the case. I want to prove that 1 plus 2 plus etcetera plus 2n minus 1, sorry, not 1 plus 2, I am taking the odd positive integer, 1 plus 3 plus etcetera plus 2n minus 1 equal to n square, and we want to prove that it is valid for every n from set of natural numbers. Okay. Now, let us go as per mathematical induction. Call this statement as P of n. We wish to prove that P of n is true for all n. How do you go about by using mathematical induction? First step is the basis step. Which demands you to verify the assertion for n equal to 1, that is to verify P of 1. The sum of first one odd positive integer, namely 1, there is no sum there, 1, and which can be written as 1 square. So, it is trivially satisfied, P of 1 is true. Now, let us go to the crucial step, namely the inductive step. Let us recall, in the inductive step, we make the assumption P of k is true, which is known as inductive hypothesis. Assume P of k is true. Meaning, assuming that 1 plus 3 plus 5 plus etcetera plus 2k minus 1, the sum of first k odd positive integers is equal to k square. And the goal is to prove, we have to prove that P of k plus 1 is true. That is, we have to prove that 1 plus 3 plus 5 plus etcetera, the k plus 1th odd positive integer, which is 2k plus 1. This is equal to k plus 1 square. This is what we are supposed to prove. As it is practice, let us start with the LHS. 1 plus 3 plus 5 plus etcetera plus 2k plus 1. Remember, the odd integer previous to 2k plus 1 will be 2k minus 1. Let me group it, 1 plus 3 plus etcetera up to 2k minus 1, let me put in parenthesis, plus 2k plus 1. Now, the first sum in the parenthesis have a formula by induction hypothesis, which is k square plus 2k plus 1 The reason it is just the induction hypothesis. K square plus 2k plus 1, which is same as k plus 1 the whole square by a little arithmetic. Thus, we have proved what is intended to be proved, the sum of first k plus 1 odd positive integers is k plus 1 square. Thus, assuming p of k is true, we establish the truth of p of k plus 1. Thus, the inductive step is complete. Hence, by mathematical induction, which we abbreviate as MI, it is true for all n. P of n is true for all n. That is 1 plus 3 plus 5 plus etc. plus 2n minus 1 is n square for every n in n. Unlike in the previous example, here we conjectured a formula and then we verified that formula using mathematical induction. Let us proceed with example. Before going to the next example, let me make one more remark. Often we may require to prove the statement involving natural number, say p of n, is true for n starting from b, b plus 1, b plus 2 and so on, where b is some integer other than 1. That is, here we are not asked to prove p of n for all natural numbers n, but only starting from b. Question is, can we apply mathematical induction? Yes, with a slight modification. And what is the modification? In the basis step, instead of proving that p of 1 is true, we verify p of b is true. And in the crucial and the second step, inductive step, we assume p of k, where now k is an integer from the set b, b plus 1 and so on. And then we prove the truth of p of k plus 1. In short, the induction starts from b instead of 1. In this context, let me give an example. Prove that 1 plus 2 plus etc. plus 2 power n is equal to 2 power n plus 1 minus 1 for every non-negative integer n. Unlike other two examples where we are asked to prove it for every natural number, here we are asked to prove this summation formula for all non-negative integer. That means the starting from n equal to 0. As I suggested in the remark, the basis step should be modified here. The basis step will be verifying that P of 0 is true. Where by P of n I mean the given statement. Okay. Let us verify P of 0. P of 0 is the LHS is just 2 power 0, which is 1, and the RHS is just 2 power 0 plus 1 minus 1, which is 2 minus 1, which is 1. So, it so easily is verified that P of 0 is true. Therefore, P of 0 is true. Now, the second step, inductive step. The induction hypothesis is the following: assume P of k is true for k a non-negative integer. What are we supposed to verify? We have to verify that P of k plus 1 is true. To show that P of k plus 1 is true, that is, we have to show that one plus 2 plus etcetera plus 2 power k plus 1 is equal to 2 power k plus 1 plus 1 minus 1. This is what we have to prove, which is same as 2 power k plus 2 minus 1. As a routine matter, let us start with the LHS. 1 plus 2 plus etcetera plus 2 power k plus 1. Notice that the term previous to 2 power k plus 1 is 2 power k. What we have in our hand is the induction hypothesis. So, let us group this 1 plus 2 plus etcetera plus 2 power k plus 2 power k plus 1. Now, the sum in the bracket by inductive hypothesis is 2 power k plus 1 minus 1, and the entity outside the bracket is 2 power k plus 1. Now, let us combine. 2 power k plus 1 is added to itself. So, you have twice 2 power k plus 1 minus 1. Now, by laws of indices, this is 2 power k plus 2 minus 1. Fortunately, that is what we are trying to prove. Hence, we proved P of k plus 1 is true. This finishes the inductive step, namely the conditional statement P of k implies P of k plus 1. That is, assuming P of k is true, we proved P of k plus 1 is true. Hence, by mathematical induction, P of n is true for all n in here it is n can be any non-negative integer. So, all n in natural number system union 0. So far, we were confining our examples on summation formulae. So, you may ask a question, can we use mathematical induction only for proving summation formulae? Answer is no. As I have told already, in principle mathematical induction can be used for proving propositions which involves set of natural numbers. In the next few examples, I would like to establish some inequalities involving natural numbers using mathematical induction. Let us continue with example, but now some inequalities. Use mathematical induction to prove that 2 power n is less than n factorial for every n greater than or equal to 4. First, I would like you to note that the given inequality 2 power n less than n factorial is not valid for n equal to 1, 2 and 3. Solution. The assertion that we want to make or to prove should be called as P of n. Let me call P of n the statement 2 power n less than n factorial. To prove that P of n is true for all n greater than or equal to 4. Let us invoke mathematical induction. Basis step. What is basis step here? It is not P of 1 is true, because we want to prove P of n is true for all n greater than or equal to 4. The basis step will be to verify P of 4 is true. What is P of 4? 2 power 4 less than 4 factorial. Is it true? Let us see. 2 power 4 is 16, which is less than 24, and 24 is what 4 factorial is. Recall that by n factorial we mean the product 1 into 2 into 3 into etc. up to n. Okay. So, for 4 factorial is 24. It verifies that P of 4 is true. Now, let us go to the second step, namely inductive step. Induction hypothesis is P of k is true. That is, we assume 2 power k is less than k factorial, where k is an integer greater than or equal to 4. We want to prove the assertion is true for k plus 1. That is, we want to prove P of k plus 1 is true. Let me write it explicitly. That is, 2 power k plus 1 is less than k plus 1 factorial. This is what we have to prove. with a little manipulations on 2 power k plus 1 and using induction hypothesis, we will be able to do this. Let us work out the details. Keep in mind that the induction hypothesis we have is 2 power k less than k factorial for a arbitrary but fixed k, where k is a positive integer greater than or equal to 4. This is the induction hypothesis what we have. Having this, let us try to achieve our goal, namely to prove that 2 power k plus 1 is less than k plus 1 factorial. Keeping induction hypothesis in mind, let us write 2 power k plus 1 as 2 into 2 power k, which follows from law of integers. And now applying induction hypothesis, this 2 power k is less than k factorial can be used here to obtain this less than 2 into k factorial. Please bear in mind what we want to achieve is 2 power k plus 1 less than k plus 1 factorial. Also recall that k plus 1 factorial can be written as k plus 1 into k factorial. Keeping that in mind, we can proceed with manipulation of the previous step to write 2 power k plus 1 less than k plus 1 into k factorial, because k is a fixed number greater than or equal to 4, which gives 2 less than k plus 1. So, using that, we can write 2 into k factorial strictly less than k plus 1 into k factorial, which is k plus 1 factorial. Thus, we achieve 2 power k plus 1 strictly less than k plus 1 factorial. Therefore, by the principle of mathematical induction, it follows that two power n is less than n factorial for every positive integer n greater than or equal to 4. This completes the solution. I will continue with many more examples in the next class. Okay, thank you so much.